In this video, we're going to discuss the basic rules of indefinite integrals, which are integrals without bounds. And we're going to discuss exponential and logarithmic integrals, and then definite integrals, which are integrals with bound a to b. So as a recap from the previous video, we know that let's say we defined fx, and this is the result of differentiating a d of capital Fx with respect to x, right? So now we know that this thing is just an inverse operation. So if we were to integrate fx with respect to x, we get capital Fx plus c. So basically, if we were to integrate capital Fx, if we were to integrate fx, we get capital Fx plus c, which c is the constant of integration. And the complete inverse operation is that if we were to differentiate capital Fx, which is the result of the integral of fx dx, we get fx, right? So this proves that these two are complete opposite operations. So let me give one example. Let's say we are asked to integrate 2x dx. What do we do? We know that if we were to differentiate df over dx, so let's say fx is equal to x cubed, we know that dfx with respect to x is equal to 2x. So we know that using this formula, we know that if we differentiate fx, we get 2x. And if we were to integrate 2x, we get x cubed plus c. And c is the constant of integration. Okay, to understand how the constant of integration arises, now imagine this fx is equal to x squared plus c. If we were to differentiate this fx with respect to x, we also get 2x. What does this show? This shows that all the constants vanish upon differentiation. So this means that there are infinite number of antiderivatives. Antiderivatives is the inverse of derivatives, and all of these antiderivatives differ by only one constant, right? That's why we get the constant of integration. So some basic rules are, obviously, if we take the integral of xn dx, it's the same thing as xn plus 1 over n plus 1 plus c. And this brings on some other theorems such as x dx is the same thing as x squared plus 2 plus c. This also tells us that a dx is the same thing as ax plus c, right? And also some other stuff like, let's say we take the integral of a fx dx. Since a is a constant, we can just bring it out of the integral. And also some additive properties. If fx and gx are added together in the integrand, we can legit factor them out. We can separate them out. These are some just very basic rules that is not that hard to grab and to understand. This is just a very basic formula to solve integrals or the integrand in the form of x to the n. And if we get integral of a fx dx, we can just factor out the a. And if there's integrands which have the sum of fx and gx, we can just separate them. So with that, we can solve a very simple problem. Let's say the question is solve the integral of 9x4 plus 2x squared dx. So here we can use result number 3. We can first split them out. Okay, so what I'm gonna do is I'm gonna split them into 9x4 dx plus 2x squared dx. Makes sense. We can just split these two functions into two different groups. Okay, so now here since this and this are just constants, we can pull them out. So here we can use, so let me make this more clear, to move from here to here, it's 3. Move from here to here, it's 2, where we can factor out a constant. So we get the integral of 9 times integral of x4 dx plus 2 times x squared dx. And again, we use the first formula, right, where x to the n is just the integral of x to the n dx is just x to the n plus 1 over n plus 1 plus c, right? So we get 9 times x to the 5 over 5 plus c. In this case, it's c1 because it's the first integral, plus 2 times x to the cubed over 3 plus c2. Okay, now you know that c1 and c2 are just arbitrary constant. They can legit be anything. c1 can legit be infinity and c2 can be infinity too. So theoretically, you can just add them up and pretend they're the same thing. So this is actually the same thing as 9x5 plus 5 plus 2x cubed over 3 plus c. Since these two result in c, it's just the same thing. Since they are arbitrary, the sum of two constants is just simply another constant. We can just loosely play with constants in general. So this is the intuition behind integrals. These are some 3 very basic rules, and this is something that you can remember. So now let's try one more example just for understanding. Let's say we get the integral of 8x9 minus 1 dx. Again, we solve it the normal way. We know that this is the same thing as 8x9 dx minus 1 dx. This uses formula number 3, right? Then we know this one is the same thing as 8 times xn dx. And this one, we can just leave it be. And here we can make use of our formula x to 10 over 10 minus x, since a dx is just ax plus c. Since this is because x to the 0 is plus 1 over 1, just x, right? That's why it comes about here. It just uses the first formula, right? So here we just use the first formula, right? So we end up with this plus c stays here. So now let's go to our second section, exponential and logarithmic integrals. So now here are 2 formulas I'm going to make you remember. So the first theorem is that for all real x is not equal to 0, we know that the integral 1 over x dx is equal to ln the absolute value of x plus c. Okay, you're like, how does this make sense? Okay, here from differentiation, we know that if you take the derivative of ln x, we get 1 over x. So same thing here. This is the first one, and the second one is theorem 2, right? What's theorem 2? Theorem 2 states that for all real constants, a is greater than 0 and a is not equal to 1, we know that the integral of ax dx is equal to ax ln a plus c. Obviously, I will try to prove this just for the understanding's sake. So let's say let y equal to 8 dx. So now we know that let's say we get y equal to ax. We know that if we ln both sides, we get x ln a, right? Now we differentiate both sides. We get 1 over y. This is because we use chain rule. We differentiate ln x first, then we differentiate y inside. So it's dy over dx. Here we use product rule. So it's actually ln a plus it's just ln a, because if we take the integral of if we differentiate ln a, it's just 0, so this is what we get. Then we end up with we know that y is the same thing as ax, so y ln a is just the same thing as ax ln a, right? So now if we make it in terms of ax, we get 1 over ln a, right, times dy over dx. This will give a. So now obviously if we integrate both sides, so we do integral of ax dx, we get 1 over ln a, since we can factor it out, dx. So this just becomes our formula, ax dx. We end up with 1 over ln a times, well, y, right, plus c. And y is just the same thing as ax over ln a plus c. We have successfully proved it. So now this one uses implicit differentiation, and I don't really expect you to know this, but just for you to understand, we know that the integral of ax dx is just the same thing as ax over ln a plus c. Okay, so now let's try some problems based on it. So I'm going to give, let's try the integral of 10x 2025 over x to 2026 plus 2025x dx. Okay, now first we use our first rule, right? Is it the first rule? I'm not sure. Yep, it's the third rule, my bad. We use the third rule so we can split them up, right? So this is the same thing as the integral of 10x 2025 over x to 2026 plus it's a dx plus 2025x dx. And now this one is just the same thing as 10 over x dx plus 2025x dx. Here we can incorporate our constant multiplication rule that helps us to bring 10 out of the integral. So now here we're going to work slowly. Here we can use theorem 1. Okay, what is theorem 1? Is the integral of 1 over x, which gives us ln x. So it's the same thing as 10 ln x, right? Plus c obviously, but we can ignore that. And this one uses 2, right? Theorem 2. That gives us 2025x over ln 2025 plus c. This is our answer. Let's try another example to understand how it works. So integrand of 10 squared over x minus 5 to the power of 3x dx. So this one is the same thing as, so now here I can just quickly go through the formulas. So this is the same thing as 1 over x dx minus 125x dx. We first split them up, in fact, to take out the 100 out of here, and this one, this is the same thing as 125x, right? Again, here we make use of our theorem 1 and this one theorem 2, right? And that gives us 100 ln x plus 125x over ln 1 plus, yeah, we solved it. So now for our last section of the day, we would like to discuss definite integrals. So as I said, I'll discuss definite integrals. So definite integrals are integrals with bounds a to b, right? So let's say we know that we have integral of f(x) dx is equal to fx plus c. But what if there's bounds a to b? What happens to this? Okay, first of all, what does bounds mean? So now currently in our integrals, we know that in an indefinite integral, let's say fx is equal to sine x. Okay, this goes on for infinity. It goes on forever and ever and ever, right? So find the area under this, an area under this, an area under this. This goes on forever, right? That's why theoretically when we plus c, it's kind of infinity, because c is literally any other constant you can perceive, right? But what if the integral has a bound? So from a to b, fx dx, what happens? So here, let's say our integral looks like this, our integral, right? But what if a to b is just from here to here? So is between this and this, right? This is what a to b means. We're finding the integral of sine x, because, well, fx is equal to sine x, is from a to b, right? In this case we do b to a because it's always subtracting that way, right? So dx, that's what it does. There is actually a finite value. There's a finite value for this. There is actually an answer for this, right? So there must be a formula for this. There should be a formula. So we give our third theorem 3. If fx is continuous, that means it's defined on the bound a to b, and if we know that fx is the antiderivative of fx. This has been discussed in the previous video. So this basically means that if we differentiate fx, we get fx, right? That's what it means. Then we know that if we were to integrate from bounds a to b, fx dx, we get f b, this capital F, okay, so this is antiderivative b to fa. So another way to show it is just actually fx, but from the bounds b to a, just subbing in. So this is what it tells. This is a way to find the answer of like of a definite integral from bounds a to b. Okay, so that's pretty obvious, to be honest. Just to understand how we use it, let's say from bound 6 to 8 and 9x5 minus 12 dx. So for now we treat it like it's an indefinite integral. So again, we use our constant multiple, we bring out a 9, we split this integral, and we know that is the same thing as 9 times the integral of, for some reason, 9 to the integral of 6 to 8 x to the 5 dx minus 6 to 8, 12 dx, right? We know that the answer is obviously 9 times x to the 6 over 6 minus 12x. But this time we put the bounds a to b, right? So in this case 8, 6 and 8, 6. There is no plus c. So if there's a plus c, there's no plus c, because plus c is where when it is a definite integral where indefinite integral where there's no bounds. But this time there's bounds, so there is a finite value. It converges to some finite value. So now let's solve it. We get this. We know that it's 9 over 6. So here we sub in 8x. So I'm just gonna change the color of the ones that I'm subbing in. 8 of 6, okay, minus 9 over 6. I'm subbing in 6 this time. Minus 12x, right? So it's just 12 times 8 minus 12 times 6, right? This is some very long algebra, but we know that this somehow converges to this massive value. We can use a calculator and solve this. But you understand how we just solved it as if it was a indefinite integral with no bounds, and we just added the bounds. It's just this formula, this graph might look like, say, like this, okay? This might look like nx to the 6 plus 5 plus c. This is the area under the graph forever, right? But if we restrict this from bound a to b, we just incorporate a and b, draw the dashed lines, and find the area between this shaded region, right? So that's why it converges to a finite value, and that's why the plus never even stays. That's why it disappears. The plus disappears. And before I go, I need to introduce two other, well, common sense things that is in par with this definite integrals with bounds. So if we take the integral of a to a fx dx is obviously 0, since if I take the graph sine x and I take the integral of between a to, well, a, the area is obviously 0. This is very intuitive. And here we can also do something called splitting. Let's say the integral of a to c fx dx. Okay, so to visualize, let's say my graph looks like this. A and c. Okay, let's say there exists, be such that a is between b and c. So there is a tiny cute little p here. Okay, so we know that the integral of a to c is, well, the area under the graph from a to c, right? But what if we just split it? Can we do from b to a fx dx plus b to c fx dx? Is it the same thing? I mean, theoretically, if we were to split this graph at b, from the bounds b to a is just this, and from the bounds c to b is, well, this, and this adds up as the integral of a to c fx dx. So this is correct. So these are some two other tiny, you could say, formula, but it's just quite intuitive and can be derivable on the spot. So hope you understand the three main stuff I have discussed in this video, which is basic rules, exponential and logarithmic integrals, and definite integrals. Hope you enjoy.